Cosmology is the study of the entire universe, and observation, as you have just learned, can take place from the 50 or perhaps it's 70 octaves of the electromagnetic spectrum which we have access, aside from that pesky 10 to 100 keV range, which will soon topple, I'm sure. And putting all that into 15 minutes seems, well, a bit of a challenge. So I have decided to use an example of a particular part of cosmology, an important part to be sure, that can be used as an example, a warning to physics students. And my example, as you might have deduced, is Hubbles Law. Hubbles Law is the seemingly simple statement that galaxies are receding from each other, and an observer on, for instance, the Earth will see galaxies have a recession velocity that is linearly proportional to their distance. Sounds very simple. V proportional to D. How simple can you get? However, as this photograph of Einstein peering through the telescope reminds us, well, it was put by William Whewell in the mid-19th century, there is a mask of theory over the entire face of nature. That is, we look outward at the universe, we observe it, but what we observe is filtered through the theories that we embrace. And general relativity interprets Hubble's law in terms of the expansion of space. There are other interpretations possible, which I will discuss. And the fact that Edwin Hubble, with his inseparable pipe, is hovering in the background of this photograph, reminds us that the statement velocity is proportional to distance is in itself an interpretation. When we look at a galaxy, there isn't a little label attached to it saying, "Hi, I'm 10 megaparsecs from the solar system, and I'm receding with a velocity of 700 kilometers per second." It doesn't work like that. So in fact, Hubble's law is interpreted, but it is in itself an interpretation of the observations. Now, cosmology I described briefly as the study of the entire universe, but it's a study that comes with its own framework. Several years ago, I attended a cosmology conference in Cleveland. I called up the conference hotel and said, "Oh, I want a special rate for the Great Lakes Cosmology Workshop." Brief silence, there's the sound of sales clerk rummaging away in the background. Finally, he comes back to the phone and says, "I'm sorry, I don't have any record of that conference being held here." I said, "Well, look again. It's the Great Lakes Cosmology Workshop. There should be a record of it." And he said, "Oh, cosmology. I thought you said cosmetology." My first response was, "I bet this never happens to Stephen Hawking." My next response was, "Well, it's actually an understandable mistake. Cosmology, cosmetology, they both come from the Greek word cosmos, originally meaning harmony or order. And so the study of cosmology assumes that, although the universe is sometimes extremely confusing to us, that there is an underlying harmony or order to the whole shebang. And cosmologists try to find that underlying harmony or order. Just like a cosmetologist tries to find the underlying harmony or order of your face, smearing away all those unsightly blemishes, the cosmologist attempts to find the underlying harmony or order of the universe by, smoothing away unsightly blemishes, like planets or stars or even galaxies. So there is an underlying order to the universe. That's sort of the beginning assumption of cosmology. And this is where I interpolate my commercial interruption. I firmly believe, and I'm going to proselytize this point of view, that every single physics and astronomy major out there should take a cosmology course as a junior or senior, because it makes a wonderful capstone experience. You're a physics major, you've done the March through Holiday and Resident, you've learned all these wonderful subfields of physics, but you've learned them separately. You've taken your course on thermodynamics and stat math, you've taken quantum mechanics, and so on and so forth through the list. But cosmology ties them all together. Perhaps not quite as well as neutron stars, which provide you with solid-state physics. But, well, of course, classical classical dynamics. How do you determine the mass of a cluster of galaxies, for instance? Well, you use the virial theorem to assume that the individual galaxies move under the influence of gravity. Or you can measure the mass of the cluster by observing its gravitational lensing effect on background galaxies. So classical dynamics and general relativity both play roles in cosmology. And of course, nuclear physics, you can apply that to Big Bang nucleosynthesis. Atomic physics, you can apply that to recombination and the formation of the cosmic microwave background. Now, and if you dare, you can go back to the very, very early universe, where there's a great deal of highly amusing particle physics going on. So all of these different fields of physics are tied up in one lovely cosmological package. And I should point out, having taught such a course myself at Ohio State, that if you ever need a review of all your freshman and sophomore physics, teaching a cosmology course really focuses your attention amazingly. This is a commercial interruption, of course, because if you should choose to teach such a course, I happen to know of an appropriate textbook. Introduction to Cosmology is in fact written at the upper level, undergraduate level. I should also point out from personal experience that if you are teaching at the 100 level to non-science majors, you can actually teach them a fairly large amount of cosmology. And of course, I taught Astronomy 143 from the esoteric numbering of the Ohio State curriculum. Starts out with a historical overview of cosmology. Now, for thousands of years, we've all been looking at the same universe. The universe hasn't evolved that much in the past 5,000 years or so, but we've developed different models for cosmology. Astronomy is based on observation, as Roger said, and our observations have become, with time, more subtle, ranging over much wider ranges of the electromagnetic spectrum, using much more sensitive instruments than the human eye. But even the earliest cosmological models, flat Earth, solid dome overhead, a la Genesis for the ancient Egyptians, or even Homer's Odyssey and Iliad, this early modeled universe is based on observation. You lived in Mesopotamia 5,000 years ago, you went outside at night, you looked around and you say, wow, what's awfully flat around here. No bumps worth mentioning on the floodplains of Mesopotamia. And you look upward and there's a fairly convincing optical illusion that you are looking at the underside of a dome. And of course, whip out the famous and much used WMAP cartoon of the evolution of the universe. Today, we have a much more sophisticated model for the universe based on many more observations. But seeing how, as the result of new observations and new interpretations, our model for the cosmos around us as well, is a very good teaching tool. Now, our models are based on observation. Our observations improve and evolve. Our models improve and evolve. And it's useful for non-scientists to know where we're coming from historically, in order to impress upon them that, cosmologists are not making all this up, Modern cosmological models do sound pretty wonky to the uninitiated. Dark matter is bound up with dark energy, something that makes the acceleration of the universe positive rather than negative. Pretty bizarre. However, within historical backgrounds, you can show how cosmologists were dragged, sometimes kicking and screaming, sometimes literally kicking and screaming, towards this model because of observations. Now, one reason why cosmology, like the rest of astronomy, is an excellent way of teaching physics is because, as people have mentioned, as people will mention, it's got that wow factor, the gee whiz factor. New observations, wow, X-rays and gamma rays and X radio wavelengths, and you can detect neutrinos, kind of. And of course, we hope in the future to detect gravitational waves, and wow, gee, gosh, golly, all of this new technology really does engage students, catches their attention. I'm not going to talk about the new gee whiz stuff.